Welcome to Brain Vision.
Spacecraft in an elliptical orbit around the Earth, and we're given the distances for its closest point in the orbit, so the perigee, point P here, and then the farthest distance, the apogee, over here. And so first we're asked to find what the period of the orbit's going to be. So part A, we want the period, and so we know from Kepler's laws that the period should be 2 pi times the semi-major axis of the orbit to the 3/2 over the square root of g times the mass of the object being orbited, so the mass of the Earth in this case. So we don't have A, but we know that this total length on the long side of the ellipse for the orbit is 2A. And so that tells us that 2A should be equal to RP plus RA. And so A then is just half of that, RP plus RA over 2. And since we have values for RP and RA, we can find that that is 8.58 times 10 to the 6th meters. And then we can solve for the period. And so we get that as 7.91 times 10 to the 3rd seconds, which comes out to be about 2.2 hours. So then part B asks us to find the ratio of the velocities at these 2 points. So it wants us to find the ratio of the velocity at the perigee to the velocity at the apogee. And it wants us to do this using conservation of momentum, or rather it gives us a hint that this would be a nice way to do it. So we know that momentum is conserved at all points throughout this orbit, since there's no external torques being applied. So that tells us that the angular momentum at point P equals the angular momentum at point A. And those momentums, because at either of these points, the velocity is tangent to the path with our radius from the point we're measuring at the mass of the Earth, the angular momentum is just going to be then the velocity times the distance there. So normally there's a sign of theta term in there, but theta will always be 90 here, so that just becomes 1. So we can write these then just as Vp times Rp should equal Va times Ra. And so we get this ratio then will just be Ra over Rp. And so that comes out to be 1.53. So that means it's moving 1.53 times faster at point P than at point A. So part C will go onto a new page. Now it wants us to find not the ratio of the velocities, but the actual values of them. And so we can do this with conservation of energy now. So really we kind of have to use both conservation of energy and conservation of angular momentum. So we're kind of just combining those two facts. So we know that energy should be conserved between these 2 points. So energy at point P equals energy at point A. I guess I've been doing lowercase a. So we can write these as the kinetic energy, so 1/2 m mass of the spaceship Vp squared, then minus or plus the potential, which is a negative term. So g mass of the Earth, mass of the spaceship over the distance, so that will be Rp. And that should equal the same term, so 1/2 m Va squared, and then minus g me m over Ra. So this is part C. So we can cancel out the mass of the spaceship right away. And then we're still going to end up with, we won't know Vp and we won't know Va. So we need another equation to be able to solve for this because there's 2 unknowns. And so that's what we've effectively done in the previous part. So we know that Vp equals 1.53 times Va. So we're just going to substitute this in for Vp here. And so then we should get 1/2 times 1.53 VA squared. So we want to make sure we square the 1.53 also. And then that'll equal, I'll move this term to the other side. So that'll equal 1/2 VA squared. And then we will have plus, and we'll kind of factor this a little, so GME, and then 1 over RP minus 1 over RA. So we get our velocities together then, and we should end up with, when we square this and then subtract this term here, we'll ultimately get 1.347 VA squared equals 2 GME. So we multiplied by the 1/2 also, and then times 1 over RP minus 1 over RA. So we take the square roots and divide by this constant here, and we'll get that VA equals 5.51 times 10 to the third meters per second. And then using this relationship, then we find that VP is 8.43 times 10 to the third meters per second. So there are our actual values for velocity, not just the ratio. And now finally in part D, so now we want the spaceship to fully leave the orbit, and we want to know what change in speed we would need at those 2 points in the orbit. So if we left from the perigee, what speed increase would we need? And if we left from the apogee, what speed increase would we need? And then which is more efficient or which takes a larger change in energy. So looking at this, we'll just use conservation of energy. So we'll say we're going from 1 point where we're in orbit to point 2 where we have left the Earth's orbit. So usually that means we're infinitely far away. So originally we have some kinetic energy and some potential energy. And then in general, we say we have kinetic and potential at point 2. But at this second point, we're saying we're infinitely far away from Earth. That's what we usually mean when we say we've left orbit. So there's no potential. And then typically we want to know like the smallest change in energy that would be needed for this to happen. So we're kind of assuming then that the velocity after it's fully left orbit is 0. Like it used all of its kinetic energy that it had in trying to get away from Earth. So that's also 0. So this whole thing is just equal to 0. So we're saying we have 1/2 times the mass of the spaceship times its velocity squared, and then minus g mass of the Earth, mass of the spaceship, over r equals 0. So we can get rid of the mass of the spaceship right away, and we should find that the velocity is going to just be the square root of 2g mass of the Earth over r. So this is just a general equation still. So this would apply to any point in the orbit. And so now we're just going to apply it at point A and at point P. So at point A, all we're doing is plugging in RA as our value for R. And we will get 8.761 times 10 to the third meters per second. And so when we compare this to the original value in orbits, we find that this has increased by 3.25 times 10 to the third meters per second. And we do the same thing for point P. So we plug in just RP for here, and we get 1.084 times 10 to the fourth meters per second. And so that is an increase of 2.41 times 10 to the third meters per second. So they're basically asking us then which of these 2 points for leaving orbit would have a smaller increase in velocity. And so that looks like it'll be point P then.